I told you if you have any doubts regarding these papers, just leave a comment and I'll discuss them. So I got two requests to discuss section B and C. So out of that request, I'll take section C and I'll try to explain the theoretical part behind these questions and how to find the answers step by step. Let's see section C. It says scientists have isolated volatile compound responsible for the special smell of babies. This has been identified as alpha isomethyl methylironone. Okay, so methylironone. Okay, so this is the compound, right? And the molar weight is given. The mass spectrum of alpha isomethylironone is shown. Okay, they have given us the mass spectrum. So that means we have to deal with mass spectrum now. So before dealing with mass spectrum, let's see what is this mass spectrum is all about. In mass spectrum, what we do here is, let's assume some elements, they have something called isotopes. Isotope means it's the same element. Like if you take hydrogen, how any element become hydrogen? It has to have a proton, one proton in the nucleus and one electron around it. So in the orbitals, there has to be electron. So if you have one proton, one electron, we call it a hydrogen atom. Having number of neutrons because neutrons are neutral particles. Since neutrons are neutral particles, having neutrons in the nucleus does not change the element. For an example, so let's take, okay, we have one proton and one electron. Okay, so this is hydrogen because it has one proton, one electron. But you can have another atom with one proton and one neutron in the nucleus, and now we have one electron here. This is also type of hydrogen because it's also hydrogen because it has one proton, one electron. You can have another hydrogen, one proton and two neutrons in the nucleus and one electron around it. This is also hydrogen. They have given special names, so they call this one protium, deuterium and tritium, but still they are still hydrogen. So those are the types of hydrogen. Only difference they have here is in the nucleus they have extra neutrons. Because of these neutrons, their chemical properties won't change because chemical properties depends on the electron configuration. So all of them has same electron configuration, their chemical properties will remain same, but their physical properties, the heaviness, they are, you can simply see the deuterium is more heavier than protium and the tritium is even more heavier than deuterium and protium. So we can see that if you take a natural hydrogen sample, actually there are three types of hydrogen based on the number of neutrons in the nucleus: protium, deuterium and tritium. Now in the nature, when you find a sample of hydrogen, we should be able to know how many isotopes we have in hydrogen and what are their percentage abundance. That means as a percentage, how much amount of protium is there, how much amount of deuterium is there, how much amount of tritium is there. To find out that, to figure it out, that we have something called mass spectrometer. In mass spectrometer, what we do here is, first we take the sample. Now here we take hydrogen sample. We keep it, we place them in a vaporization chamber. Vaporization chamber means is a place where you take the sample in and you heat it up. The purpose of this one is if your sample is a liquid or a solid. If it is a solid or a liquid, you simply try to evaporate it and make a gaseous sample. So that's what you're going to do in the vaporization chamber. Then what you're going to do is, then you're going to send them to the atomization chamber. So in atomization chamber, what we are going to do here is, we know that hydrogen comes as hydrogen molecules. How they come as hydrogen molecule? Hydrogen molecule means two hydrogen atoms together. They have a covalent bond. So they come out as a hydrogen molecule. So when they come out as a hydrogen molecule, what will happen here is, we have to break these bonds. When we break these bonds, only we will get hydrogen atoms. That's our plan. So what we are trying to do here is, we are going to break the bond to get individual hydrogen atoms. So that's what we are going to do in this atomization chamber. After we go through this atomization chamber, what we are going to do next is we are going to send them into ionization chamber. In the ionization chamber, what you're going to do is we take these hydrogen atoms. Now we have three types of hydrogen atoms. You can have hydrogen protium atoms, deuterium atoms, and tritium atoms. For our understanding, I'll draw protium in purple color, deuterium in red color, tritium in green color. Then what you're going to do is these are neutral atoms. So neutral atom is, if you take a hydrogen atom, we have the nucleus and we have one electron in the first energy shell. So what I'm going to do is in the ionization chamber, I have an electron gun. So using this electron gun, I'm going to shoot electrons at this hydrogen atom, high energetic electrons, very fast. So because of this high energetic electron, what will happen when this electron hit this hydrogen atom, it will make sure this electron which is already in the hydrogen atom will thrown away from the hydrogen atom. So when the electron hit this atom, the existing electron also will thrown away. So we call this is bombardment of electrons. As a result of that, our hydrogen atom will lose electron. When we know that when an atom is losing electron, we call it's ionized. So what we have is ionized hydrogen atom. So we have protium which is ionized, deuterium which is ionized, and tritium which is ionized. Actually, you have to understand this one. To this atomization and ionization both take place in one chamber. All these three things take place in one chamber. How they make the vaporization? By heating. How they make this atomization and ionization? Both by heating with high energetic electrons. We are going to shoot high energetic electrons into these molecules that will make sure they will break their covalent bond, as well as the atoms will get ionized. Okay, so after they are ionized, what we are going to do next here is we are going to send them into an accelerator. In accelerator, what we do here is now we have positively charged ions now, protium, deuterium, and tritium. Then we are going to do is we have two metal plates. This side it will become positive and this side it will become negative. So we know that positive and negative attract each other. So all these ions will attract towards this negative plate. But this is a porous plate. There are small holes in it. So any H plus ion who cannot land on this plate, what will happen to them is they will end up entering the next chamber with high speed. So we call accelerator, that's why we call it accelerator. Accelerator has simply an electric field where they accelerate these ions towards the next chamber. Right. When these ions enter the next chamber, we have a magnetic field. What magnetic field going to do? We know that when the charged particle travels to a magnetic field, they will get deflect because there's a force acting on this charged particle. So same thing what happens here. We have protium, deuterium, tritium, all three are charged particles. So I'll just put the positive charge in purple color on top of protium and positive charge on top of the deuterium and the positive charge on top of the tritium. Why I drawn them as I have drew them as these vehicles? I'm just showing them how heavy they are. So you can simply see protium is the lightest one. It has only one proton and one electron. So I just draw it like a motorbike. Deuterium is the second heaviest one. It has one proton, one neutron, and one electron. So it's like a car. Tritium is the heaviest one. It has one proton, two neutrons, and one electron. So when these three moves through this magnetic field, both have the same charge, +1, +1, +1. So because of this magnetic field, there will be a force on them, but it's the same force. Why? Because all of them has the same charge. When they have the same force on three different objects with different masses, their deflection is different. So lightest one deflects. So this protium is supposed to travel on this straight line, but it will get deflected because of this force by a huge angle. Can you see? It's a large angle. Then this deuterium supposed to travel on this line. Again, because of the force, it get deflected, but not as much as protium. Tritium supposed to travel on this path. It also get deflected, but not as much as other two. So therefore, based on their mass over charge ratio, they will be, depending on their mass, they will get deflected. And after they deflected, what will happen? They will land on the detector. So detector will measure how much they have deflected, and based on that, detector will use the computer program to calculate their mass over charge ratio. So since their mass charge is +1, so it's simply they will locate in the position of their mass. And the number of collision, how many ions collide on this detector, tells us the percentage abundance. You can see there are more the more protiums, so therefore what will happen? That peak will go really high, and deuterium and tritium, their peaks are very low. That means the percentage abundance of those two are very low. That's the basic concept of mass spectrometer. Now let's see how we can use this concept in our question. But one thing we have to understand here is, we discussed that in the atomization and ionization chamber, we are hitting the molecule with high energetic electrons. But when you are hitting the molecule with high energetic electrons, you can't expect all the molecules will break into atoms. This is a mass spectrum of bromine sample. We know that bromine comes out as Br2 molecules. Two bromine atoms covalently bonded with each other. But can you see we get peaks here also? Because the reason is some of the molecules will break into atoms. So therefore you get individual bromine atoms. But some of the molecules will remain as molecules. So therefore what will happen? They will give a peak as the whole molecule itself. So therefore the whole molecule will give us the peak in the most right corner of the graph. So when you look at the graph, in the most right corner, we get the whole molecule giving a peak. We call it molecular ion peaks, because we can't expect all the bonds to break when you hit them using electrons. Okay, now let's see with this one. Now they're saying that the mass spectrum of our molecule is given. Okay, they have given the mass spectrum. Describe how fragments are formed in the mass spectrometer. We know how they are formed. We hit them using high energy molecules to break the bonds. That's because they're asking how fragments. Fragments means atoms or pieces of molecules. A molecule will break into pieces when you hit them with electrons. So we can write high energetic electrons. Okay, we can write here high energetic electrons are fired or shoot at the molecules in order to break the bonds between atoms. That's how we break the bonds. Now let's see the marking scheme. Marking scheme given. First point is given, electrons are fired at the molecules. Yes, fired at the molecules. First mark is, I got the first mark. By breaking the bonds. Yeah, break the bond between atoms. Yes. So we get 2 marks for this question. So we get full marks. That's how we answer the part A. Now let's go for next one. The most abundant peak is at mass over charge is 136. Draw the possible structure of the fragment of alpha isomethyl ion causing the peak at 136. Okay. This one, so we have to do something like this. So usually this is a common question. They will ask you to draw these structures. So first of all, I just take this alpha isomethyl ion molecule and I just fill the blanks. Fill the blanks means like this. I'm going to draw it. So we know that here there's a CH3 group. So I'll just write it's a CH3. I'm just going to draw the structural formula. Here this is also CH3 group. CH3. Because carbon has to have 4 bonds. I can see only 1 bond. So other 3 should be hydrogens. Then it should be carbon atom here, but it doesn't have any hydrogen there. So these two CH2 groups attached to a carbon atom. That carbon atom attached to another carbon atom here. Okay, 6 carbon atoms are there. 1, 2, 3, 4, 5, 6. And there's only one double bond here. Okay, so this carbon atom has 4 bonds, no problem. This one have 3 bonds. So that means it has 3 bonds, means it has to have another hydrogen should be there. So the 4th bond. This one has 1, 2, 3. So this also has to have hydrogen. This one 3. So this has to have hydrogen. This one has only 2. So this should be CH2. This one also CH2. Right. Then this side we have carbon with double bond. So it should be CH. Then here also carbon. 4 bonds are there, so it cannot have any other bonds. Here this bond ends here, so it should be CH3 group. Here should be CH3. Here there's a carbon atom, double bond oxygen. It has all 4 bonds, and this should be CH3. So I just drew the structural formula of the molecule that I see. Then what I'm going to do is, we put the mass. Carbon is 12, no, hydrogen is 1. There are 3 hydrogens. So 12 plus 3 is 15. This group is 15. This is also 15. This is 12, 1 carbon atom. This is CH2, it's 14. This is CH, is 13. This is CH2, is 14. CH, it's 13. 1, 2, 3. This one cannot have hydrogen because the reason is it has already 4 bonds. So this simply 12. This is CH. Does it have? Yes, it is CH. So it is 13. This is 15. This one is 13. This one is 12. This one is 12. This is 16. Oxygen molar mass is 16. This is 15. This is 15. Right. Now when you're coming to 136, so we have to start from one corner. So you have to be real good at math, or otherwise you can use the calculator. So 15 plus 15, I'll just add these two. 15 plus 15 is 30. 30 is there. 30 plus 12 is 42. 42 plus 14, 56. 56 plus 14 is 70. 70 plus 13 is 83. 83 plus 12, 95. 95 plus 15, 110. 110 plus 13, 123. Very close. We need 136. No, 123 plus 13. 123 plus 13 is 136. Yes, am I correct? Yes, it's 136. That means if I take this, if I break the bond from here, I'll get a piece of 136. That's the fragment they want us to find. Okay, so in this one I'm going to break the bond from here. Okay, so how I'm going to draw the fragment? So it should look like this. So my fragment should look like, they want structure of the, draw the possible structure. So we just draw the possible structures. You don't have to draw this structural formula in this diagram itself. You can do it, but I did this one to make sure that you can understand the structures. Okay, so what I'm going to draw here is, I'm going to draw that part. So there's a double bond here, and these two parts are there, and this part is there, and from here it stops. That's where I'm going to stop my structure. So then what I'm going to do is, I put the square bracket, then I get the positive charge, because the reason is, in mass spectrum we know that only positive charge species will give you a peak, because they will only get deflected in that the magnetic field. So you can remember, in the mass spectrum there's a deflector. No, in the magnetic field only the one with positive charge will get deflected. So therefore I'm going to add this positive charge. So let's see the answers. Yes, so that's one of the answers we have. So we have the answer, so you get 1 mark there. So since it's 1 mark, you have to do this one within 1 minute. So it's better to like practice this, adding masses and put them in a structure. Okay, let's go for part B. Alpha isomethyl iron can be synthesized in the laboratory. 1 mole of geraniol reacts with 1 mole of butanol in this synthesis. Okay, so we have some compound called geraniol and they have another compound called butanol. Calculate the maximum mass of alpha isomethyl iron that can be produced from 25 kilograms of butanol. So one thing I have to tell you here is some students, when they see this structure alpha isomethyl iron and butanol, we know it, geraniol, you get very scared because we haven't seen these structures. Actually, these structures is not for you because every curriculum, now for an example, let's assume one student is doing a national curriculum of their country, and when sometimes they might compare the national curriculum papers with these Edexcel papers. So actually those kids, when they are find out that we are doing very easy things, they might like feel where they will look down on us. So actually these structures are not for you, right? For the people who are comparing this paper with their national curriculum or some other curriculum, these structures are for them. So these structures for them to make sure that they will get panicked, not for you, right? So even you don't know these structures, just stick to the basics. There's nothing hard. Only these structures are put them to like make sure that this paper looks very standard and make sure that others get scared, right? Not for you. Okay. Now they're asking, calculate the maximum mass of alpha isomethyl iron that can be produced from 25 kilograms of butanol. They have given us very easy reaction. So they say that this geraniol and butanol, they react with each other. 1 mole of geraniol reacts with 1 mole of butanol in this reaction. Alright, 1 mole reacts with 1 mole gives you 1 mole of alpha isomethyl iron. That means their reacting ratio is 1:1. They're asking, calculate the maximum mass of alpha isomethyl iron that can be produced from 25 kilograms of butanol. We are using butanol. How much? 25 kilograms. We don't deal with kilograms, so we go for grams. We know that it's 25 means 1 kilogram is 1000 grams, so we are talking about 25,000 grams. We can't deal with mass when you're talking about reactions, so we have to find the number of moles. So number of moles of butanol equals mass divided by molar mass. What is the mass of butanol? We just have it. It's 25,000 grams. 25,000 grams. The molar mass of butanol, we have to do it. So this is CH3, which is 15, then CH2, which is 14, then here there's a carbon atom, and this is CH3, then again 15, this is 12 and 16, so 15 plus 15, 30 plus 14. Okay, so our answer is 72. So 72 grams per mole. Okay, if you have to divide 25,000 by 72, when you divide by 25,000 by 72, we get 347.22 moles. Okay, we know the number of moles. What is the molar ratio? 1:1. So if I use 1 mole of butanol, I will get 1 mole of product. So if I use 347.22 moles of this butanol, I will get 347.22 moles of our compound alpha isomethyl iron. Now they don't ask the number of moles, they ask mass. So how to find mass? If number of moles equals mass divided by molar mass, so mass equals number of moles times molar mass. Number of moles, we know it, 347.22 moles multiplied by molar mass of this compound is given 206. So when you do this calculation, your answer will be, I'll just write the answer here where we can see it clearly. It is, I'll write the answer somewhere here where we can see clearly. So we can see the answer here is 71,528 grams. So they ask the mass in calculate maximum alpha. Yeah, this is our answer. Or we can write in kilograms, 71.528 kilograms. Both answers are fine. Okay, let's see the answer. Okay, calculate the moles of butanone, 347.22. We just found it, is 1 mark. Then calculation maximum mass of alpha isomethyl ironone, it is 71.528 kilograms. Yes, we have the answer. So we got the answer for part B. Right, up to now is so easy, very simple questions. They have to find the number of the basic equation we have learned in AS level. Number of moles equals mass divided by molar mass. Then they're asking calculate the atomic economy of the reaction. We can remember we just discussed this reaction. When geraniol react with butanone, we know that we get this alpha isomethyl ironone product. They're asking the atom economy. Atom economy equation is molar mass of the desired product. What is the molar mass of the desired product? You take the desired product divide by molar mass of all the reactants into 100. That's atom economy. Okay. Desired product. What is our desired product? Is alpha isomethyl ironone, which is 206 grams per mole. We divide by molar mass of the reactant. Butanone, we just found it is 72. So 72 is one reactant plus what is other reactant? Geraniol. So we have to do the calculation. So this is 15. This is 15. We have 4 bonds. This is 12. This is so we have 3 bonds. So it's 13. Yes, CH now. This is 14. This is 14. Here we have 1, 2, 3, 4. This is only carbon. So 12, 15. And then here also we have 1, 2, 3. So it's 13. Then 1, 2, 3. This is 13. So I'm just adding the masses. So likewise, then we have oxygen atom, which is 16. Okay. So when you add all these values, our answer for the question that molar weight is 152. Okay. 72 plus 152. So grams mole will cancel out and multiply by 100. Our answer is 91.964%. So we can round it up into 92%. Why we round it up? Because the reason is usually your answer cannot have, but here they don't talk about the specific significant figures. But only thing you have to know is when you are writing an answer, your answer cannot have more significant figures than your data. If your data has 2 significant figures or 3 significant figures, it's better to go round up your answer for 2 or 3 significant figures. But here having 1, 2, 3, 4, 5 significant figures is a little bit higher than the data, so it's not acceptable. But I don't think here they won't do anything because they haven't told about number of significant figures here. So our answer is 91.964. They have accepted 92% also. Yes, that's fine. So calculate the atomic economy of this reaction. We just did it. It's also a simple calculation. Okay. Now let's go for next one. Scientists have also isolated some of the compounds responsible for the smell produced by teenagers. The samples were collected from many individuals, separated by chromatography and identified by mass spectrometry. Many compounds were present in both infant and teenager sweat, but in different ratios. Some compounds in teenager sweat were not found in infant sweat. These compounds include the molecule A and B. Okay, they have given us 2 molecules A and B. I don't think even the question they tell something else story question should be very basic, especially focused in our curriculum. A high performance liquid chromatography HPLC column is packed with material that has amine group attached as shown. Okay, we have this one. State which of these molecule A or B would take longer to move through the column. Justify your answer. First, we have to know what is this HPLC. HPLC is like this. In a high performance liquid chromatography, what we are going to do here is we take our sample put it on a column. This is like column is like it's actually like a burette. You can think it like a burette. A liquid mobile phase, we call it liquid yellow. So we have this mobile phase and it's mixed with our sample. Now we are going to pour it from the top, right? Now when this mixture go through it, now when we pour it there, we have to have the stopwatch here. So after you pour it there, now we place it with the mobile phase and our sample. Now let's assume this mobile phase is red color one, so it's keep on passing through this. It's like jelly like beads, we call it polar beads. So actually what will happen, so it's the same what they have shown here. This bead is the same thing what they are shown in this question. You can see this stuff, and they say that in these beads they have NH2 group pointing outward. So let's assume this bead also has that NH2 group pointing outward. So what they are saying is this NH2 will form interaction with this mobile phase which is passing down as well as the sample. So sample I'll draw it in green color. So this is the sample I'm showing. So if some molecule is forming more attraction with this gelatinous beads, so this polar phase, what will happen is they will come down very slowly. So one point you will see your sample is coming out from here. First what you will see is when you check it, you can see that it's not the sample, it's only the mobile phase. Sample is not here. So then you have doubt. Then after some time you see, after some few minutes or few seconds, the sample will also start coming out. So that means the sample got delayed. Why? Because it formed this attraction with this polar solid particles. So this time delay we call it retention time. From the retention time we can identify what is this sample is. So there are data booklet. Using the data booklet, when the sample get delayed than the mobile phase, that delayed time we call it retention time is a reading to identify this sample. That's the basic concept of it. Now they are not asking that much stuff. That's out of these two, state which of the molecules A or B would take longer to move through the column. Justify your answer. Alright, now they are asking out of these ones, which one will take longer to move through the column. Justify and what is the reason for that delay. That's the question they are asking. Okay. Now we know that obviously both will form interaction with this polar beads. Why? Because they are so oxygen atom. We know that here we have nitrogen and hydrogen covalent bonds. We know that nitrogen and hydrogen is highly polar covalent bond. So this is extremely plus delta. This is extremely minus delta. So therefore this plus delta can attract this oxygen atom. Is a permanent dipole-dipole interaction, and this can also attract this oxygen atom. But there's something special, because we know that if you have these atoms, nitrogen, oxygen, fluorine, NOF, attached to a hydrogen atom directly, between those groups they can have intermolecular hydrogen bonds. Here I can see oxygen atom attached to a hydrogen atom, and here nitrogen atom attached to hydrogen. So this is plus delta and this minus delta is extreme version of plus and minus. So between these two molecules, B and our polar molecules, what will happen? Polar beads, they will have hydrogen bonds. So this is a hydrogen bond. Hydrogen bond is stronger than permanent dipole-dipole interaction. Therefore, who will spend more time? Because B molecule, because it will get strongly attracted to this polar parts, polar NH2 parts than the other one. So this one is stronger. Okay, now how I'm going to write it? They're asking which of the molecule A or B would take longer time to move through the column. So we said first we'll say B molecule, because I'm answering the question they are asking. First one is which molecule? Okay, A or B. First I said B molecule. Justify your answer. Why? Because then I can write because B will form form stronger intermolecular forces with the amine group in the column. Amine group in the performance packed with the material. Okay, amine group in the material packed in the column. It's better we tell what is that attraction also. So we say that it's a hydrogen bond. So we can say that OH group in the B molecule forms hydrogen bonds with NH2 group in the material. Okay, let's see the answers. So answer says molecule B, yes, because B will form, yes, we say that which one, yes, our answer is correct. Molecule B, we have mentioned it, yes. Strong attraction, yes, form strong intermolecular forces is the same as attraction. OH can form stronger hydrogen bonds, yes. OH group in the molecule will form hydrogen bonds with the NH2 groups. So we have all the points, so therefore we get full marks for this question. Name the different column chromatography technique that could be used to separate A and B. Other than HPLC, what is the other technique that you can use in here? Right. Let's see what is the other chromatography we have. Other than HPLC, they are asking the column chromatography. Otherwise, we have something called paper chromatography, but they are saying specifically in the question, we need column chromatography, not anything else. So other than HPLC, what we have learned is something called gas liquid chromatography. We call it GLC. What happened in gas liquid chromatography? We have a carrier gas. Okay, so what we do is from this carrier gas, we are passing this carrier gas in a tube through inside an oven. The best carrier gas is helium and argon because those are noble gases. They don't react. If we don't have some GLCs, they use nitrogen, but we do not recommend nitrogen. We only recommend noble gas because they are highly inert. When these gases are going there, they have something called injection port. From there, we are going to place our sample. So we place our sample. Now sample is the one which is in red arrows. Now when our sample get mixed there, now it's slowly moving inside these tubes inside the oven. When they are moving through these tubes, what will happen? Heat get absorbed into this gas as well as our sample. But in the wall of these tubes, they have, just like that polar gelatinous beads, we have some polar stationary phase applied on these tubes. So what will happen if our sample is more polar, it will get attached to this polar stationary phase. That means if they get attached to this polar stationary phase, they will spend more times in the oven. When they spend more time in the oven, they will absorb more heat. Then what will happen? If you know the time you inject this sample into this system, and from the detector, if you know when they go out, how much amount of heat they have absorbed, if you know the time, and if you know how much amount of heat they have absorbed, then we can find many properties of the sample. Their specific heat capacity, their thermal conductivity, all these properties. From that, they can identify that sample. That's what we do in gas liquid chromatography. So they're asking a question. Name the different column chromatography technique that could be used to separate AB. We know that is gas liquid chromatography or gas chromatography is what they're expecting. Even if you write GLC or gas liquid chromatography, it is a allow answer. Allow means yes, it is accepted. The only things when you're looking, go through the marking scheme, only thing you have to remember is, if you see something like ignore, you might see a point, ignore this point. Ignore this point means they ask the examiner just to pretend like they didn't see that point, because it doesn't harm your answer. So when you write an answer, if you write some wrong answers, it might change the meaning of your answer. So they call it ignore it. But sometimes they call it reject. Reject means they say that if that point is there, you have to reject. They will not give marks for the whole sentence. There's a reason why they put this reject. Let's take an example. I'll take a very basic one, right? Now this question. State which of the molecule A or B would take longer to move through the column. Justify your answer. Then you might try to, okay, these points are there. Then you can write another point. There's permanent dipole. There is dipole interaction with molecule A. Is it wrong? No, because molecule A can form permanent dipole interaction with this NH2 group. So they might say that in the marking scheme, ignore this one, because it doesn't matter for our answer. He say ignore. Just if you see it, just pretend like you didn't see it. So this is the ignoring point. Writing such points is not harmful. Only thing is you are wasting your time. But sometimes you said molecule B, and because it will form strong attraction with the amine group, then you might be say that molecule B, and it might be molecule A also. Might be molecule A. That means they are asking very straightforward question. What is your question? A or B? You have to write either right A or B. You said molecule B and it might be molecule A. So that means you are being tricky. You said A, B, and in some case if it is A, I write A also there. Then my answer has A or B, no? So they have to give the marks. No, they know that it either be B or either A. So in such point they say reject. They say that reject if you say molecule A. Why? When you say molecule A, that whole sentence will not get marked. Even you have written molecule B, you will not get marked, because you know that is fair, right? Because you can't get marks for like writing both B and A. So that's the marking scheme, how they build it, right? So only thing is, if it is accept, yes, it is accepted answer. So in our case, we have that answer as accepted, GLC and gas chromatography. So that means it's a valid answer. You don't have to worry about it. Let's go for next one. Some of the compound isolated only from the teenagers were carboxylic acids. The solubility in water of two of these acids is shown. So they have solubilities. So I can see what they are saying here is, this one only dissolves very less, 0.13 grams in 1 cubic decimeter. But this one dissolves more, 25 grams in 1 cubic decimeter. Explain how the structure of acid affect their solubility in water. So we can see that both are carboxylic acid, no? So carboxylic acid, we know that they have this COOH group. COOH group means they have OH group. This carboxylic acid also have COOH group. That means they have OH group. In water molecule, we have two OH groups. It has OH group. So that means we know that they can form intermolecular hydrogen bonds with each other. So I can first point write both carboxylic acids can form hydrogen bonds. Okay, I wrote the first point. Then 3-methyl butanoic acid, 4-ethyl octanoic acid. Octa means 8, but this is 4. Obviously we can see that the top one has more number of carbon atoms. We know that when you have more number of carbon, this is how it works. If you take carboxylic acid, we have R group and then COOH group. So we know that usually COOH groups, they are polar groups. COOH groups are polar. So they can form intermolecular hydrogen bonds or permanent dipole-dipole interaction with water. But R groups are nonpolar. They only form London dispersion forces. Since they only form London dispersion forces, they can't mix with water because water doesn't want to form London dispersion force because it has two OH group. So it won't form hydrogen bonds. So therefore, this when the R group become bigger and bigger, we know that top one has 8 carbon. 8 carbon means this R group is very long. When the R group is big, the non-polar parts get bigger and bigger. When the non-polar parts is bigger, it doesn't want to mix with this polar molecule, which is water. So therefore, we can see that larger hydrocarbon has low solubility. So we can write larger hydrocarbon chain lower the solubility of 4-ethyl octanoic acid. Okay, larger hydrocarbon chain lower the solubility of 4-methyl octanoic acid. Because why? Because when larger the group, these non-polar groups become bigger. Therefore, they form stronger London dispersion force among those molecules. The reason is because large hydrocarbon chain forms stronger London forces between each other, molecules, right? Forces between each other molecules. So that's the answer. I have 3 points. I think my answer is correct. Let's go for the marking scheme. Both carboxylic acid can form hydrogen bonds with water. Yes. First one, I have the first mark. The larger the non-polar chain and the lower the solubility. Larger hydrocarbon chain, lower the solubility of. Yes, larger the chain, lower the solubility. Yes, both are there. Because the London forces between large molecules are stronger. Yes, because the London forces are stronger between each molecule. Yes, we have all 3 points. So that means we get 3 marks. Okay. The things in the bracket, they are not compulsory. So because I can see in the bracket due to them having more electrons. The things in the brackets are accepted, but they are not must to have in the point, right? So if I have written it, is very good answer. But I'm trying to manage the time because we have to stick to 3 minutes time and everything. So that's why I'm just trying to focus on things. But even you write these things is very good, right? It will be a very good complete answer. So that's the thing. But here we got all 3 marks. Now let's move to part 2 of this question number D. Part 2, the Ka for 3-methyl butanoic acid is 1.58. Okay, 3-methyl butanoic acid. I don't want to draw this structure, but I know that it's butanoic acid. It's a carboxylic acid with R group. Okay, R group is there, COH group is there. So when this acid get ionized, get dissociate, what you get is RCOO minus plus H plus. Some likes to put that water molecule and write it as H3O plus, but I like to write it like this. So it's up to you, right? Okay, so this is the one. K for this one is calculate the pH of the solution of 3-methyl butanoic acid. Okay, now we have a problem. Do I know their concentration? They have given me some clue. 25 grams in cubic decimeter. 3-methyl butanoic acid has 25 grams in. So they say the concentration of this one is, we have 25 grams in 1 cubic decimeter. That's the point I have. keeping that one in my mind, so I'm going to next one. Okay, now I know the mass. Now what I have to do is, concentration means number of moles in 1 cubic decimeter. If I can convert these grams into moles, I'll get the concentration. Number of moles equals mass divided by molar mass. What is the mass? 25. Right. Then that's the mass. Molar weight of this 3-methylbutanoic acid. Molar weight of 3-methylbutanoic acid. I think we have to do the calculation. For that we have to draw the structure. Okay, 3-methylbutanoic acid. So butanoic acid means 4 carbon. In the 4th carbon we have the CH group. Okay, 1, 2, 3. 3rd carbon there's a methyl group CH3. So this is also CH3. This is CH. This is CH2. Okay. So we have 15 times plus 15 is 30. 30 plus 13 is 43. 43 plus 14, 47, 57. 57 plus CH group. Our answer is 102. Okay, so 25 divided by 102 grams per mole. My answer is concentration of RCH group is we have it there. Okay, 25 divided by 102. Now what we are going to do is, let's assume, so this is the concentration, right? Okay, C concentration is there. Okay, so I'll just erase this part. Okay, now I know the concentration, right? Concentration is 1 cubic decimeter. So I'll just rewrite the concentration of this one, because there's a lot of work here, so it get mixed up. So concentration C equals, in 1 cubic decimeter we have 25 divided by 102 moles. Okay, shall we do the calculation? And 25 divided by 102, will I get decimal values? So anyway, I'll do the calculation and see. 25 divided by 102 is hard to do the mental math, so therefore we'll use the calculator. Okay, using the calculator, if you find 25 divided by 102, 25 divided by 102, our answer is, there are plenty of decimal values. It is 0.245 moles per cubic decimeter. Okay, I found the concentration. Okay, now then what will happen? Now this carboxylic acid will dissociate in water. No, how do we find that? So I have 0.245 moles per cubic decimeter of this carboxylic acid. How much will dissociate? I don't know. Let's assume X amount dissociate. X dissociate. When X dissociate, 1:1:1, no, I'll get X amount of this carboxylate ion and X amount of H plus ions produced. So we know that K expression equals, Ka equals concentration of the products. Concentration of the products is H plus concentration times RCOO minus concentration divided by RCOOH concentration. K value, do we know K value? Yes, it is 1.58 into 10 to the power minus 5. Do you know the value of H plus? X. Do you know the value of RCOO minus? X. So this is simply X squared. What is in the bottom? It's 0.245 minus X. Okay. From this calculation I can find X. So we'll find X here. So X equals, okay, so we get 0.0019679 moles per cubic decimeter. That's X is the H plus concentration. What they're asking? They are asking us pH value. We know that pH value equals minus log H plus ion concentration. So when you place this value, we'll get the pH value is 2.706, or we can simply say that 2.71 is our pH value. 2.706, or we can write 2.71 is our pH value. Let's check the answer. Our answer is, okay, so we'll go for our answer. Okay, so our answer is yes, 2.71. This is our answer. That's correct. So we get the full mark for calculation to write in the Kc expression. Sorry, Ka expression. That's done. Ka means Kc means Ka means actually Kc expression for acid. Find in the value of yes, x. Yes, that's our next one. Then we get the final. So this is the correct answer without no working scores 3 marks. So if you have done the correction with the calculation properly, and if you get the correct answer, that's also you get full marks. Then we'll go to next part. Okay, now they are saying that one of the compound present in the sample from both teenagers and infants was 6-methyl hept 5-ene 2-on. Draw the skeletal formula of 6-methyl hept 5-ene 2-on. Okay, now they expect us to draw the skeletal formula of this molecule. Okay, so we are going to write the skeletal formula of this one. Before that, I think it's better for us to draw the structural formula. Okay, let's see. Hept means 1, 2, 3, 4, 5, 6, 7. Okay, we have 7 carbon. Obviously they get linked, no, so I just link them. Okay, so this is my carbon chain 7, so that's hept. 6-methyl 1, 2, 3, 4, 5, 6. Okay, 6 carbon, there's a methyl group CH3. 6-methyl hept 5-ene. In the 5th carbon there's a double bond 1, 2, 3, 4, 5. There's a double bond starting from 5 to 6. 5-ene 2-on 1, 2. 2nd carbon there's a carbonyl group. Okay, so this is CH3. This one has 4 bonds, so this should be CH2, CH2. This is CH. This is 1 to 4 bonds are there, so this is CH3. So they are not asking the skeletal formula, they are not asking structural formula, they are asking the skeletal formula. This is how we convert structural formula into skeletal formula. Wherever you had the carbon atom, keep dots 1, 2, 3, 4, 5, 6, 7. Show the bonds 1, these bonds. Whenever you see hydrogen atoms, don't respond. No need to draw any hydrogen atom which is attached to the carbon atom. There's a CH2 group, that means there's a carbon atom here. There's a double bonded oxygen, you have to show that one. There's a carbon-carbon double bond, you have to show that one. Okay, this is our skeletal formula. So we just drew the skeletal formula for this molecule. Yes. Let's see the marking scheme, whether we drew it correct. Yes, carbon oxygen double bond. Yes, it's perfect. Okay. Now let's go for next one. What is the next part of the question? Next part is the infrared spectrum of 6-methyl hept 5-ene 2-on is shown. 6-methyl hept, that's the one we drew. Yes, 6-methyl hept 5-ene 2-on. Give the bond and wave number range of the 3 absorption in the spectrum that are not in the fingerprint region. Use your data booklet. First, we should know what is this IR spectrum. IR energy is like this. We know that we have something called, I'm just teaching you this part in a very basic, because we don't have time to do it, because we are just discussing the paper in a very basic way. If you take electromagnetic radiation, we know that we have different range. Visible range is the one we can see. What visible range can do is can perform transition of electrons between energy levels. If there's a 1 electron here, if there's another empty shell here, you can just shift this electron from one energy level to another one. That's what we can do. That's what the visible range can do it. But if you go for next one, this X-rays, gamma rays and UV rays, they have more energy than this visible light. They can remove this electron not between energy levels, they can remove this electron completely away from the atom. They can ionize it. They have more power. But we are going to little bit lower than that. We know the visible light, we have that color range, no? violet, indigo, blue, green, yellow, orange, red. Okay, so we have this one. So actually in this one, violet is the one in this corner, the high energy end. So that's why we call this is ultraviolet, above violet. Red is the low energy one, so it comes here. So one below red, we call it infrared. Infrared radiation, they don't have much energy, not even to shift the electrons between energy, not even to ionize. What they can do is they can vibrate electrons which are in a chemical bond. So when you hit infrared radiation, what will happen in a chemical bond? The electrons start vibrate. Vibrate means like this. Actually, they are shifting. Let's take two atoms, two A atoms, having pair of electrons sharing exactly in the middle. Because of this infrared radiation, they get a little bit energy. Sometimes this pair of electrons from the midline, it can shift towards this side. Then what will happen? This atom A realize it pulls this electron back to it, towards it. Then what will happen? When it pulls the electron towards that, again the electron pair now little bit goes towards this atom now. Then what will happen? Other atom realize it pulls it back. So they will keep on back and forth moving between these two atoms. So it's just like a spring. So therefore, instead of writing a covalent bond, I will draw a spring like this. Between hydrogen atoms, there are only one pair of electrons. I show it using a one spring. Between oxygen atoms, there are two pair of electrons. So I show two springs. So when I send IR radiation, I know that these pair of electrons will absorb energy. They will start vibrating. I'm showing IR radiation using these three lines, but we can't see IR rays in naked eye, but I use this three line to show the IR radiation. But we know that the energy required to vibrate one spring should be different than energy required to vibrate two spring, because two spring is a little bit harder, you need more energy. That's what we get. So we can see that here the first line and the third line is being absorbed from this hydrogen covalent bond. But here first line and the second line is being absorbed from this oxygen-oxygen double bond. So it shows that different bond absorb different amount of IR radiation. That's what the detector going to detect. It's going to see what is the absorption, and if we have data booklet, if we have done this absorption earlier, if we have those readings from the absorption values, we can figure it out. What was the bond here? There was a hydrogen single bond. What was the bond here? There was a oxygen double bond. But in our syllabus, we are mainly focused on polar covalent bonds. Why? Polar covalent bonds are the one who gives us a strong absorption where we can detect. For an example, this is how the graph we do it. On the y-axis, we show how much is absorbed. On the x-axis, we give something called wave number. Wave number is simply, wavelength. 1 over wavelength. That's what we call wave number. So let's assume if there's no absorption, the line will go like this. But suddenly, if there's any bond, there will be a strong absorption. From that drop in the peak, we know that there's something, a bond. Usually this type of strong absorption is given by polar covalent bonds. For an example, if I have carbon-oxygen double bond, it will give me absorption between 1850 to 1750 in this region. I can see a very sharp peak because of this carbon-oxygen double bond. So when there's a polar covalent bond, we see this absorption value. From that, we can identify from the reading where we get that absorption, we can identify by referring the data booklet what are the bonds available in that molecule. Right. There's another thing called fingerprint region. You know that if you take human fingerprint, let's take you look at the fingerprint, you look at your fingerprint and one of your friends close by. When you look at it, is same, it's like looks same, it's like some circles are there. But the thing is, they are different from each other, but you can't identify on the naked eye. They can be only analyzed using a computer scan. So by computer program, they can detailly analyze and then they identify whose fingerprint is this one. There are two different fingerprints. This is A fingerprint, this is B. So there's a region in this graphs also. There are a large number of peaks appears very close to each other. So usually this happens when the wave number is less than 1300. In that region, there are peaks. They are slightly different from each other. So naked eye cannot identify it. So we call that region which is fingerprint region. We don't worry about that part. We only worry about the region on this side above 1300. Those are the ones we can make readings easily. Okay. Now I have the page of the data booklet and I have the question again. The infrared spectrum of 6-methyl hept 5-in-2-1, I have the structure here, is shown. Give the bond and wave number range of 3 absorbance in the spectrum that are not in the fingerprint region. Use your data booklet. Okay, so it's 2 marks, but I'll write all the things I can see. I can see here carbon oxygen double bond, right? Carbon oxygen double bond of a ketone. Carbon oxygen double bond of a ketone, I have it. Okay, carbon oxygen double bond of a ketone, alkyl ketone here. I have it 1720 to 1700. So I can write first one is carbon oxygen double bond between 1720 to 1700 per centimeter. The unit is here, wave number per centimeter. I just put a bracket. Okay, yeah, per centimeter. I just put the bracket there to show that it belongs to both of them, per centimeter. For the ketone, yes, for ketone. Then I can see here carbon double bond. So I can write it here. Carbon double bond between carbon double here. Isolated alkene, arene is an isolated alkene, between 1669 1645 per centimeter for alkene. Then other than that, I don't see any other stuff, but I can show this one. Carbon hydrogen bonds are there? No, is carbon hydrogen carbon bonds I don't see in the one, but I have carbon hydrogen in alkane, so that's alkane. So I can write carbon hydrogen between alkane is 2962 to 2853 per centimeter for alkane. Yes, I see 3 peaks. Let's see the marking scheme. Yeah, is there anything we missed? No, let's go for the marking scheme. Oh, I missed this one. In alkene oil also there we have a carbon hydrogen bond, so I just missed it, but let's see. 3 correct absorption are right. We have 3 now. Yes, 1 2 3. Are they correct? Carbon oxygen double bond between 1720 and 1700. Yes. Then carbon double bond between 1669 to 1645. Yes. Then carbon hydrogen between 2962 to 2853 for alkane. Yes. So we have 3 peaks. We get both marks. Right. Okay, so we have done discussing the section C of Unit 4 paper. So I think we are done with the. If you have any more requests, just leave a comment. Then I'll do that. I'll fulfill that request also. Thank you very much for joining with me. And if you have any doubts, just leave a comment or don't forget to subscribe. Then whenever I release a new video, you are the first one to get to know it.